Okay, we're back. So we're going to now discuss the general topics about reciprocal, linear, and reciprocal quadratic functions. So the key ideas, what are they? First of all, the first key idea is all the y-coordinates of a reciprocal function are the reciprocals of the y-coordinates of the original function. So, for example, we had the vertex 0, 9, and it converted itself to 0, 1 over 9. So the only part that gets the reciprocal is actually the y values, not the x values. The x values stay the same, folks. It's the y values that get reciprocated. Next part. The graph of the reciprocal function has a vertical asymptote at each 0 of the original function. So remember that we had a 0, and let's look at the back to the graph that we just had. And we're going to come back to this idea in a second. Let's look at the graph. So the original function, this blue graph, was the parabola. Now, the vertical asymptote was created where the graph hits the x-axis. So the original function where it hits the x-axis. So we have vertical asymptotes at both x equals -3 and x equals +3. All right, back to the next page. Way too much writing here, folks. Just a second. So here we go. The graph of the reciprocal function has a vertical asymptote at each 0 of the original function. Next part. A reciprocal function will always have a horizontal asymptote at y equals 0 if the original is linear or quadratic. Alright? Now remember, when we look at the other functions, so we're going to go back to the previous screen to look at the graph to see this. So let's go back to the next screen. Here we go. When we look at it, the horizontal asymptote is going to be here at y equals 0. Why is that the case? Looking at the equation, you can see here that the equation is 1 over something. That means this numerator is a number. And it can be a very, very small number, such as here or here, but it can never equal 0. So this function will never, ever equal 0. As a result, because it will never equal 0, what we're going to be doing is we can always draw a horizontal asymptote for this type of function. All right, let's go back to this general description page. Here we go. Last bit. A reciprocal function has the same positive, negative intervals as the original function. Let's go back to the previous graph so that I can explain that again. So this is important, this last statement. It has the same positive, negative intervals. That means the graph will stay positive in the positive area and stay negative in the negative area. So let's look at the previous graph so that we can understand that. The original function, the blue graph, was positive here in this section, and therefore the black graph is also positive. Positive, I mean it has the same, not the same, but it has positive y values. It stays positive y values irregardless of whether you take the reciprocal or not. Okay? So positive remains positive, and negative over here remains negative on both sides. So the intervals of positive, that means y values that are greater than 0, and intervals of negative, where the y values are less than 0, remain the same. Let's go to the general screen again. So again, a reciprocal function has the same positive, negative intervals as the original function. Let's move forwards to the next part. Intervals of increase or decrease on the original function are opposite from the original function. All right? So, they're going to be opposite each other. Let's go back to the graph and look at the graph so that we can describe this properly. So we're going to the back to the graph. Here, it talks about increase and decrease are opposite. Here, this section over here, the graph was increasing originally, the blue graph. The black graph is now decreasing. Let's going from here to here, the graph was originally increasing. Now the black graph is decreasing all the way up to where the vertex was, and we took the reciprocal. From here, the original graph was decreasing, so the new function is actually increasing. All right? And last but not least, you have the function decreasing over here, and the new function is actually increasing. So we look at the entire graph, we look at this entire function. This particular function is doing opposite of what it was originally. Other than the areas of positive and negative, everything else we notice that we're doing opposite. So increasing is decreasing, so here it was increasing, the function is decreasing. From here the function is decreasing, so our new function is increasing. And finally the same goes over here. So this is what we're looking at. Let's go back to the general ideas. All right? Now, so very important this one. Next part. If the range of the original function includes 1 and or negative 1, so what that means is if the graph actually can have a y value of 1 or a y value of negative 1 and or, meaning one or the other or both, okay, both would be ideal, what we can say is that the reciprocal function intersects the original function at these points. So these have a common point, all right? They're the same point. Let's look back at the graph to note that. So we're going to go back to the graph again so you can see this. Back to the graph. And you can see that by these points that I made here, where the graph intersects the y value of 1, which is here and here, both graphs will intersect at that point. And the same goes over here, at negative 1 as well. So it intersects at negative 1, so both graphs will intersect there. Don't forget that when you're looking at the graph and you're drawing it, I'm going to be looking for where your graph intersects at negative 1 and making sure that both graphs intersect there. The same here. What you will be required to do is give me the exact values as well. And remember, we did have the exact values on the previous page. So I'm just going to go back to the previous page and note that here are our exact values, and you will have to list them as important characteristics of the reciprocal function. All right, let's go to the screen where the original, we talked about this. All right, so a little bit too much writing there, folks. So 1 or negative 1. Let's keep going with this idea. If the original function has a local minimum point, then the reciprocal function will have a local maximum point. All right, and this works both ways. If the original function has a local maximum, then the reciprocal function will have a local minimum. So I'm just going to rewrite those there for you. Okay, but remember that it's not the x value that changes, it's only the y value. So we're looking at reciprocals of those values and what happens. All right. If you're not sure what I'm talking about there, let's go back to the graph so I can rephrase that again. So we're going back to the graph, and remember that this particular parabola had a local max way up here. You can see him here. And this maximum turned into a minimum on this graph. It's called the local minimum because notice that there are minimums going on either side. It even goes even lower. So this is known as a local minimum because in this area there would be a something would happen here, i.e. the slope of the tangent line at this point would actually be 0. So again, if the original graph has a maximum up here, then the reciprocal function would have a minimum. All right, well, that's the end of that information, folks. Let's go back to that last page. So it's very important that to note all of these key ideas, whether it be this page or this page, that you understand how to generate the graph of a reciprocal function, especially if you're given the original function and then you have to flip it over. there's going to be important features that we're going to be looking for. Alright, hope this video helps, guys. Take care. Have a good night. Complete the homework.